Okay, today we're starting a new chapter, Chapter 3, Section 1, Relations and Functions. And I've looked over this section, and this is a monster of a section. So prepare to probably watch this video 2 or 3 times because your brain's going to be so tired of hearing me talk, you're going to need like a 30-minute break. You need to cut this off into sections because this is a monster section. Because there's a lot to digest here. So this might just, I don't think, whatever, we'll do this. We'll see if it's any good. Say I looked over it, I didn't say I read it all, right? All right, so functions appear all around us and are a fundamental part of mathematics. Functions occur when one quantity depends on another. Here are just a few examples. The revenue generated by selling a certain product depends on the number of items sold, right? The volume of a cube depends on the length of an edge of the cube. For a person who works by the hour, the gross pay depends on the number of hours worked, right? These are all functions of well, it depends on, I guess, the variable here. But if you think about it, you can probably come up with the countless situations where one thing, event, or occurrence depends on another. Before we officially define a function, we must first define a relation. Okay, so I'll keep that here. And let's see if this will fit. Do some moving around. Okay, so here we go. All right. So now let's define what a relation is, okay? So a relation is a correspondence between two sets, A and B, such that each element of set A corresponds to one or more elements of set B. Set A is called the domain of the relation, and set B is called the range. And hopefully you've heard the terms domain and range before. If not, you're definitely going to be familiar with them by the end of this lecture. So let's actually go back to the beginning of this definition. A relation is a correspondence between two sets A and B. Okay, so the two sets A and B, they don't have to be different. Okay, now we're going to see here in a moment they will be different. You know, we have the set A is the names of people, and set B is their weight, right? But a lot of times what we do is we use set A to be the real numbers, right? We plug in a number into a function, and then set B is also the real numbers, okay? So they don't have to be two different sets. They can be the exact same set. We just need to define what those sets are as we proceed. Okay? So this reads, suppose that Adam, Patrice, and Scott are college roommates and their weight are 180, 190, and 180 respectively. The pairing of the roommates' names with their weights is a relation, right? We're relating the name with the weight. In this example, we're relating a set of names with a set of weights. The set of names Adam, Patrice, Scott is the domain of this relation, whereas the set weights is the range, right? That's all there is to it. It's relating one thing to another. Relation, relate. The words are right there, right? Maybe I should have, we'll put it on a new page. I was going to say maybe I should have put it on the current page or put them together, but I think this will be just fine. Okay, so a relation can be represented as a set of ordered pairs with the elements of the domain listed first. The previous relation can be written as a set of ordered pairs, and the domain, Adam goes to 180, Patrice goes to 190, Scott goes to 180. Now, if we switch the domain and range of this relation, then we have this. 180 goes to Adam and Scott, 190 goes to Patrice. Okay. This one here is okay. I don't really like it, so we're gonna skip that. Okay, so before we get to that, let's talk about something real quick, okay? So, in math, we know that we come up with equations, right? we have equations. That's just math, okay? All right. Well, a subset of an equation would be a function. Let's see here, a function. That's terrible. Function. All right, so again, I don't know if I've said it to this class or not, but I am left-handed. And as a lefty, I'm a very heavy-handed writer. Meaning, I usually put my hand down on like my entire hand on the paper. I know many righties probably do it as well, but I know like the correct way to write, is you just kind of pinch your pencil in a triangle, and then you write over the paper. But I can't put my hand down on this tablet, otherwise it goes crazy. Not that you asked, but now you know. Anyway, so we have an equation, and then a subset of an equation would be a function, and then a subset of a function would be a one-to-one function, which we'll talk about later. And then a subset of that will be an inverse, which again we'll talk about later, okay? But that's kind of the flow chart of what we're looking at, all right? So basically what this means is that, all equations, well, no, all functions are equations, but not all equations are functions. And I feel like we get a little too deep here, so we're just gonna pause there, and I might reference this whenever we do get to that point, because at least I introduced it right. So let's just stop there. Anyways, let's go. Definition function. Okay, so a function is a relation such that for each element in the domain. Okay, so this is important. For each element in the domain, there is exactly one corresponding element in the range. Okay, so for each value in the domain, one value in the domain. Okay, values that we're used to in domains are, when we graph, are integers, right? 1, 2, 3, 4, 5, 6, right? For each element in the domain, there is exactly one corresponding element in the range. Okay, so what that's saying is that you can only go to one element in the range from one element in the domain. Now, here we go. This is why I said today's gonna be a monster. So we're gonna dial it back just a hot second, and we're gonna look at this. Oh, slide eraser. We're gonna look at this with some handy dandy drawings, as well as some ordered pairs. Okay. So let's look at A real quick. So A, looking at the domain. This is the domain. Look at the domain. Does every element in the domain go to exactly one element in the range? Okay, so this only goes to one. Perfect. This only goes to one. Perfect. It's the same one, but it only goes to one. Perfect. And this only goes to one. Okay, so all that is perfect. Now, A would be a function. Okay, but let's say, for instance, just to give you an idea, this would not be a function if, and I guess this might just be height, so we're just going to roll with height, okay? So this would not be a function, and let's think about this logically. If Phoebe was 5'5", and if Phoebe was 3'1", that doesn't make sense, does it? Right? So if A is a function of people's height, okay, it would have to follow the laws of function, and it does, that one person has one height, right? But if we violated what the function is here, then we would be saying that Phoebe is both 5'5" and 3'1", and of course that doesn't make sense, does it? Okay. B, 0 goes to 7, 3 goes to 7, negative 2 goes to 7, and 6 goes to 7. They all go to 7, okay? It's the exact same 7, okay? But again, they're all only going to one value in the range. That's the whole point, okay? So A and B, they are indeed functions. C, all right, C is a little bit different now. Here, yeah, C is a little bit different now, okay? So these are ordered pairs, okay? It's a set of ordered pairs. And what we're looking for here, and if you want to, let's go ahead and draw this out. We'll put D and R, okay? So the domain, are the set of all x values here, okay? So we would say 3, -3, -4, 1, and 3, Okay, and the range that corresponds to that would be 7, 2, 5, 4, and -4. Okay, so what this is saying is, 3 goes to 7, -3 goes to 2, -4 goes to 5, 1 goes to 4, and 3 goes to -4. Okay, but let's see here. So 3 is repeated. Okay, so I could kind of this here. I could erase this 3 because I don't need to write it twice, do I? Okay, but so instead I could do this. Okay, so if we have little arrows here. Okay, 3 is going to a +7 and it's going to a -4. Okay, since that 3 is going to 2 separate values, I can tell you that C is not a function, okay, because the definition up here reads that for each element in the domain, which is this, for each element in this domain, there is exactly one corresponding element in the range, okay, so it only goes to one element in the range, here rather, okay, but as we see, the +3 goes to 2 separate values, so C does not express a function. Okay. Now if we look at D, honestly, here's what you really have to do is just look at the domains. So there's 1, 0, 1, 2, and 3. Oh, I'm sorry, -1, 0, 1, 2, and 3. And we don't even repeat x's at all. Okay. So since we do not repeat the x's or the domain, then there's no way that we can have a domain go to 2 ranges. So D is also a function. C is the only one that is not a function. And that's just the answers to what I said. Okay. I'm gonna go ahead and snip this entire example here and just talk about it from there instead of look at the graph and doing things on my own. Okay, so excuse me. Use the domain. I probably shouldn't have done it, Mike. Should I have? All right. Anyway, I'm sorry. Use the domain and range of the following relation to determine whether the relation is a function. Okay. So what we would be doing is we would be plotting these points, right? So if I go left 4 units and up 5, I would have the point -4, 5. If I went left 2 units and up 2 units, I'd have the point -2, -2, +2, and so on and so forth. Okay. So if I were to list off that set of ordered pairs, which would be this, again, it's just the dots on that graph or on that plane. The domain is -4, -2, 0, and 1 of all those points. All right, and then the range is -2, 0, 2, 4, 5. Okay, so if we were to look at these ordered pairs, notice that we have a -4, we have a -2, we have a 0, we have a 1, and we have a 1 again. Okay, so we repeated x's. Now, in order for this to be a function, those x's, those 1s, have to go to the exact same one. Okay, only one corresponding value in the range. Well, one of the 1s goes to a -2, and one of them goes to a 4, and that tells me right away that this does not express a function. Okay, it could be an equation. That's fine. It could be an equation all at once, but it does not express a function, and that's kind of what this is all about. That maybe I jumped the gun on, but I'm gonna leave it there anyways. Okay. So that's that. Since we repeat x's and those x's go to different values, we cannot say that they are a function. Right. So that's what that looks like graphically. Excuse me. So let's look at it algebraically. I think I could snip all that. So page. Okay, so this reads, in example 2, we see that a finite number of ordered pairs, right, so the little dots that we saw, right, in the Cartesian plane can represent every relation. Relations can also be described by infinitely many ordered pairs in the plane. I don't know if I should have snipped that, but here's what we're really getting at here, okay? So example 2, we looked at things graphically. At least that's what I feel like we're trying to get to. Maybe not, but I'll talk about this anyways. So in example 2, we kind of look at things graphically, okay? And we'll come back to it here in a moment. But in mathematics, we look at things graphically, and it sounds like what it is. We look at things on a graph, and then we look at things algebraically, which means that we look at them in terms of an equation. Okay. All right. So example 3, we're going to be looking at equations, and we're going to be determining if they do indeed represent y as a function of x. Okay. So what does that mean? Well, realistically, we should jump straight to C maybe to really drive the point home, but we'll do A, B, and C just in order. Okay. So A, what I'm going to do is I'm going to solve A for y. Okay. So if I were to subtract 3x from both sides, I would have negative 2y is equal to negative 3x minus 12. And if I divide both sides by a negative 2, I've got y is equal to 3 halves x plus 6. Okay, and of course we saw that we've seen in the previous section, previous chapters, I guess, that this is just a slope-intercept form, right? We can tell that the slope is 3 halves and that the y-intercept is 6. But that's not what we're looking for right now. Okay, instead, example 3 is wanting us to determine whether the following equations represent y as a function of x. Okay, so that means, is it a function? Okay, so if I plug in an x value, how many y's do I get back? Okay, so I only want to get one y value back when I plug in an x. Okay, so let's go back and look at these. So if let's say c is some function, okay, and if I plugged in a 3 here and a 3 here, notice how I get two separate values, right? If I plug in a 3, I get a 7. If I plug in a 3, I get a negative 4. Okay, so that was not a function, correct? Same thing could be said for the points here at 1. If I plugged in a 1, where was it at? If I plugged in a 1, I would get a negative 2, and if I plugged in a 1, I would get a positive 4. So I'm getting two separate values. Okay. Well, if I plug in an x here, okay, doesn't matter what x I put in, I'm always going to get one value back, always. Okay. And let's go ahead and also go ahead and write out b. And I actually don't have to write out b, right? B is already written as a function of y, right? If I plug in one value of x, I get one value of y back. And again, real quick, I feel like if you're lost, C will really drive this point home, 100%. Okay, so let us solve for y. Okay, so here we go. I'm going to have y squared is equal to, and it's going to be a negative x plus 3 quantity squared plus 16. Okay, and yeah, that happens, okay? And so now I'm going to want to take the square root of both sides. So I'm going to have the square root of y is equal to, if I take the square root of both sides, it has to be a plus or minus square root of, and then a negative x plus 3 quantity squared plus 16. Okay, we're going to stop right there just for now. Okay, so if I plug in an x value here, okay, if I plug in some x value here, right, and let's plug in negative 3, right? If I plug in a negative 3 there, right, well, negative 3 plus 3 is 0, 0 squared is 0, negative 0 is 0, so that just kind of knocks that out, right? All right, so then we just have the square root of 16, okay? So we would have plus or minus the square root of 16, which we know is plus or minus 4. Okay, so if I plugged in one x value, I would get two y values out, right? Because that plus or minus is plus or minus right there. Okay, so algebraically, that's how I can tell if an equation is a function or not. This right here, 100%, full stop. If I plug in some value of x, this tells me that I'm going to get two values of y, because I'm going to get a positive value of it and a negative value of it. Okay, and that's it. So A, as we said, you can plug in any x value there, you'll get a different y value out. B, same thing. C, and C, like I said, was really the one that drove the point home because of this plus or minus there. Okay, so that's how we look at things algebraically. So we looked at things kind of graphically, and then we looked at things algebraically. Now let's see if we can look at things super graphically, if that is next. Nope, it's not next. Let's see. Could have sworn. Nah, okay, not quite yet, but we'll get to there. So this looks like a lot to digest. Let's see. So it reads, in example 3, we see that the equation 3x minus 2y is equal to negative 12 could be explicitly solved for y to obtain that function, and that's what we did. When an equation is explicitly solved for y, we say that y is a function of x, of course, or that the variable y depends on the variable x. So what does that mean? So the variable y depends on the variable x, okay, and then of course this leads into independent and dependent variables. So, and this is actually pretty good because I did it with C here. Okay, so with C, I said, hey, you know, imagine we plug in a negative 3 for x, and then we would get back y is equal to plus or minus 4. Okay, so keep that in mind. I plugged in negative 3, and I got plus or minus 4. Okay, so where are we at? We say that the variable y depends on the variable x. So that plus or minus 4 that I got as a solution on the previous example, the plus or minus 4, depended upon me picking negative 3 as the x. Okay? And you can say that I independently chose the number negative 3. Okay? And then since I chose the number negative 3, I got plus or minus 4. And therefore, the plus or minus 4 was dependent upon the variable 3 that I chose. Okay, hopefully that makes sense. I independently chose negative 3. I chose it for a reason, right? Because I wanted to just kind of make that go away. But I independently chose it. I can choose any number. I can choose. Well, 17 probably wouldn't be the play there. But I could choose 1, right? I choose 1, and if I plugged in a 1 there, 1 plus 3 is 4. 4 squared is 16. And, well, that's actually not a good example because I would just get one value. 2, 5, 25. Yeah. Yeah, we're gonna stick with not talking about that one just yet. Okay, it's a lot more complicated than that, especially if I especially if I try to use integers. Anyways, where am I at? Independent, dependent variables. Independent variables, you independently choose them. Again, these are very aptly named, right? Dependent variable is the variable that depends upon the variable I choose, the independent variable. So basically, y is dependent upon the x value, and that's how it is. Okay, so maybe I should read on, and they can say things a lot more eloquently than I can. So instead of using the variable y, instead of using the variable y, letters such as F, G, or H, and others. Okay, so this whole entire paragraph here, what it's trying to say is that you know, up until now, whenever we choose a variable, right, the most common variable we choose is x, right? And you know, some other variables we choose are y. We call z. You know, we'll say a, we'll say b, we'll say c, so on and so forth. Okay, these are variables to you know, a number, right? What we're going to do now is we're going to call these functions a name, okay? And the base name is f. That is the base name of the function, right? Or maybe like the default name, just such as the default variable is x. I would say find x, right? And you would go do some algebra and figure out what that value of x is. Find out what the variable's value is. All right, that was us naming the variable. So basically it's like this. If we had x plus 3, okay? If we didn't use a variable, you know, we might say question mark, right? Question mark plus 3 is equal to 9. Okay, well, question mark plus 3, that sounds kind of silly, right? But so that's why we use a variable. Instead of saying question mark plus 3, we would say x. Okay, same thing with the function here. Okay, instead of calling this function, you know, just any name, right? So like instead of saying, you know, gravity function. Actually, Yeah, we'll just call it gravity function, okay? Instead of saying gravity function is equal to something, you know, all we have to do really is just instead just say, you know, gravity function is big G of x. And that's it, okay? So same thing with variables, we name functions. Sometimes I feel like I over-explain things, sorry. Let's see. In our example, if f of x equal to 3 halves x plus 6, okay, so all that stuff again. Let's look at the relationship between this real quick and this. Okay, what's the difference here? Well, the difference between these two is that this top one is a y and this bottom one is an f of x. Everything else is the exact same. So what does that tell me? Okay, well that tells me that y and f of x are essentially interchangeable. Okay, and that makes sense because if I were to look at an ordered pair, okay, if I was talking about an ordered pair, I know my ordered pair is some x and some y. Okay, well I can also say that that ordered pair is some x and the function at that x. Okay, so let me explain that real quick. If I have f of x is equal to 3x plus 4, okay? Well, let's say I plug in a 1 for x. If I plug in a 1 for the x, let's try this again. Then I would get 7, okay? So I would have the point 1, 7. Okay, so that's essentially what I'm doing. So this 1, 7 would be a point on this graph, okay? But its notation can also be looked at as x and f of x. And we're going to be seeing that here in a moment, how we can evaluate functions at some value. And honestly, I guess this is pretty much what I was trying to say there. We'll put the new page. Okay, so if we have the function here, let's do it in red. If we have this function, f of x equal to 3 half x plus 6. If I plug in a negative 4 into this equation, okay, and for x, and then I do the arithmetic, what I would get out is a 0. So my point on the graph, I plug in negative 4 for x, then I get 0 out, so I would plot that point there. And then that would be, I would repeat that procedure for the rest of these numbers, and then I would get these values of y out, and I would plot those points as well. Okay, so this reads, use function notation. So rewrite these equations using function notation where y is a function of y is a function of x. Then answer the question following each equation. Okay, so let's just start right off with A, and I'm going to rewrite this in terms of, you know, y is equal to something. So it's going to be a negative y is equal to negative 3x plus 5. I'm going to multiply both sides by negative 1 to make my y positive. So I've got y is equal to positive 3x minus 5. Okay. And then once I get to that point, I'm going to rewrite this equation. Okay, it says rewrite these equations using function notation. I told you before, y and f of x, they're essentially interchangeable. Okay, so I'm going to rewrite that as f of x is equal to 3x minus 5. Okay, so that was me rewriting the equation as a function of f. Okay. Well, yeah, function notation. So then the second part, okay, the second part here, what is the value of f of 4? Okay, so what am I going to do here? Well, what I'm going to do is I'm going to evaluate this function at 4. Ooh, man, my 5s are getting killed today, aren't they? All right, so anyways. So 3 times 4 is 12. 12 minus 5 is 7. So f of 4 is just equal to 7. And that's it. Okay, so I evaluated the function at this value, f of 4, and then I just did the arithmetic. 3 times 4 is 12. 12 minus 5 is 7. Okay. Next up, and we'll do it in blue again. Okay, so, okay, actually, I guess I do have to. So this says, rewrite these equations in function notation. So if I were to rewrite this equation in function notation, it looks like, again, I'd have to solve for y, right? So if I solve for y, let's see, so we'd have negative 2y. Actually, let's just go ahead and add the 2y to the other side. How about that? Okay, so if I added the 2y to the other side, I would have x squared plus 1 is equal to 2y. Okay, now I'm just going to flip everything, just left side to right side to left side, right? So I'm just going to say 2y is equal to x squared plus 1. I'm going to divide both sides by 2, so I'm going to have y is equal to 1 half x squared plus 1 half. Okay, and then I'm going to rewrite that as f of x is equal to 1 half x squared plus 1 half. All right, that's it. And kind of, I'm a little bit short on room here because my toolbar's down there. You can't see it in the YouTube video, but it is. So actually, I don't think I need to do that. Okay, so okay. So anyways, so this says, does the point negative 2, 1 lie on the graph of this function? Okay, so what this is asking us is if I plugged in a negative 2 for the x value, how do I know it's negative 2 for the x value? Well, this is an ordered pair. Okay, the ordered pair we know are in the form x, y, right? Talked about that on the previous slide. Well, if I plug in negative 2 for x, I should get 1 for y when I'm done. Okay, and so if I were to go ahead and do this, let's plug in negative 2 here. And we're going to kind of do this in our head, okay? Because again, I'm kind of out of room there. But if I plugged in a negative 2 for x, okay, well, let's do this. What is negative 2 quantity squared? Well, negative 2 quantity squared is 4, okay? What is 4 times 1 half? 4 times 1 half is 2. 2 plus 1 half is 2.5. And 2.5 is not the one that we were looking for, okay? So we would say that, this point does not lie on the graph of this function, so no. Okay. And C is a tricky one. So C, let's solve for y. So y is equal to negative 7. Okay, so first of all, if I were to graph this, what would it look like? Okay, well, it would look like a horizontal line at y is equal to negative 7. So at y is equal to negative 7, we have a horizontal line. And this tells me already that, it's not going to be passing through 3, but let's go ahead and finish this thought process out, okay? So this is saying, what is f of x when x is equal to 3? Okay, well, if I were to solve this like I do any function, what would I do? Well, I would plug in 3 for x. Do you see an x here? No, so I can't plug in 3 for x if an x does not exist, right? So, excuse me. So it just does not exist. So f of 3, oh yeah, I forgot to write this in function notation, I'm sorry. F of x is equal to negative 7. Okay, so if I plugged in 3, f of 3, I'm plugging in that 3 everywhere where I see an x in this equation, which is literally nowhere. So f of 3 is just negative 7. Okay, and that's it for that one. Whew. Man, I think we're just not halfway through. It's told you it'd be a doozy. Oh, okay. So here's where we get to a doozy. No, I'll go ahead and do this. All right, so we're definitely going to need a second page, I'm sure of it. Okay, so here we go. A. F of 0. Okay, so F of 0. So what I would do is I would plug in a 0 everywhere where I see an x in this equation. I'm sorry, I didn't even read the equation. I'm sorry about that. Okay, so, or the problem. So given that f of x is equal to x squared plus x minus 1, evaluate the function. Okay, so we're going to evaluate this function. Okay, A says that f of 0. So what I'm going to do is I'm going to plug in 0 everywhere where you see an x. Okay, so it'll be 0 quantity squared plus 0 minus 1. Well, 0 squared 0 plus 0 is 0 minus 1, so that is negative 1. Hey, that was actually pretty easy, wasn't it? Okay. All right, so B is f of negative 1. So we're going to say f of negative, let's try that again, negative 1. Okay, so I'm going to plug in a negative 1 everywhere, so it's going to be negative 1, quantity squared, plus negative 1, minus 1. Okay, so what's negative 1 squared? Well, negative 1 squared is 1. 1 plus a negative 1, well, 1 plus a negative 1 is 0, and then 0 minus 1 is negative 1. Okay, so that's good. We're well on our way here. Now, C is getting a little more complicated. So let's do that. So what is f of x plus h? That's horrible. Let's do that again. F x plus h. All right. Well, I'm going to plug in x plus h everywhere where I see an x. Okay. So previously, I've just been putting in, numbers where it tells me to put in numbers and things like that. This time, it's telling me to put in x plus h. Well, you do it like you think you do, right? So I'm going to put x plus h everywhere where there is an x, where there's an x in my equation. So x plus h quantity squared plus x plus h minus 1. All right, well, what is x plus h quantity squared? Well, that is x squared plus 2 times a times b, so that's plus 2xh plus h squared plus x plus h minus 1. We're going to combine like terms. Do we have like terms? We don't have like terms. Okay, so we're done actually there, okay? So that is C. X squared plus 2xh plus h squared plus x plus h. So that's x of x plus h. Now D. Here we go. All right, we're going to go ahead and we're going to re-snip this so we know what we're looking at. Okay, so we're going to try that again and put it on a new page. Okay. So D is wanting us to have f of x plus h minus f of x. Okay. Well, lucky me, I did f of x plus h already, right? And it's right here. So no, not new page. Wait a minute. What did I do wrong? Okay, can I delete this page? Let's see. No, that's not it. Okay, I'm trying to think here. All right, let's go back. Here we're going to do. We're going to. I guess we're just going to have to snip this. We will put. Oh no. Yeah, we'll put this on a new page. Okay, so this is my new page. Okay, so I'm going to move this here, and I'm going to snip this again. Sorry, I haven't actually done something like this with this program yet, so I was trying to get my ducks in a row here. So current page. Perfect. There we go. Perfect. Okay. So again, recap because I'm mumbling here. We're trying to do D. D is f of x plus h minus f of x, okay? Lucky us, we did f of x plus h right here, and this is it, okay? So we just have to say that's f of x plus h, and then minus f of x. Well, what's f of x? Well, f of x is right here. So minus x squared plus x plus x minus 1, and that is all over h. This is going to be a problem. Okay, so here we go. Actually, it's not going to be too bad. Instead of rewriting this entire numerator here, okay, what I'm going to do is I'm going to go ahead and, I'm going to distribute this negative through this through those parentheses there, okay? So it'll be a negative x squared minus x plus 1. So negative x squared minus x squared minus x plus 1. Okay, perfect. All right, now we can combine like terms. So this x squared and this negative x squared, they cancel. This negative x and this, that positive x and this negative x cancel. This negative 1 and that positive 1 cancel. And that looks about it. So what I have remaining will be 2xh plus h squared plus h all over h. And I've got an h in every single term here in my numerator, right? So I can factor an h out. So I factor an h out. I've got 2x plus h plus 1 all over h. I know that these h's can cancel. So that means I've got 2x plus h plus 1. Okay? And that was D. Big old doozy there, wasn't it? But again, let's recap, because I feel like I haven't touched on these in a minute. So A, all I did was plug in these values, f of 0. I plugged in 0 into my equation. Oh, well, let's see here. I plugged in 0 into my function up here. And then I just evaluated. A and B are pretty easy. C, I then evaluate at a value, right? I evaluated at x plus h. And so I plugged in x plus h everywhere where there was an x in my original function, and I got this, and then that was f of x plus h. Well, looking at D, it's saying f of x plus h. Well, I already did it. It was here, okay? And so that's where this mess comes in. So it was f of x plus h minus f of x, which was this. This is f of x. And then I just did my arithmetic that I am abundantly used to now. That's fine. And I end up getting 2x plus h. All right, this equation isn't, it might be random to you, I guess, but this is the difference quotient, and you will come across that in, I think we talked briefly about it in pre-cal, but definitely in calculus. So let's see, do I have anything on the next page? All right, good. Here we go. I think this would be pretty good. This is useful. You could read that on your own, but it's pretty useful, I think. Ooh, okay, so this is where you can kind of turn your brain off just a tad during the lecture, right? We talk about a lot of stuff today, so we'll put that up here. It's right here. All right, so without reading the lines above, the main takeaway here is the vertical line test. Okay, so earlier I mentioned that in order to tell if something is a function algebraically, we solve for y, and then we determine do we have that plus or minus there. Okay, and if we have that plus or minus there, then we do indeed, or we do not have a function. Okay. That's how we check things out algebraically. How we check them vertically is, vertically. How we check things algebraically, graphically, okay, sorry. How we check things graphically is so much easier because all we do is look at this vertical line test, okay? And I feel like the vertical line test is just one of those things that, doesn't matter how long you have been out of school, you just kind of remember it. And if you don't, sorry to offend you. But the vertical line test, a graph on the Cartesian plane is the graph of a function, okay? If and only if no vertical line intersects the graph more than once. So if I can throw out a let's see here. If I can throw out a vertical line, yeah, that's good. So example of vertical line. So looking at the red line here, that's the graph, okay? So if I were to take just a vertical line and just intersect wherever the heck I wanted to, I will not touch that graph more than once. So I will not touch the graph. Again, the graph is the image, the red line, okay? I will not touch that graph more than once. But for the second graph, depending on the vertical line I choose, if I choose the vertical line over here, right, I'm not going to cross at more than one point. But if I chose the vertical line to be right here, well, then I'm going to cross that graph in 3 places. And since I cross it in more than one, it is not a function. Okay, so let's go ahead and look at this. New page. Use the vertical line test. So looking at this graph, A, B, and C. Is A a function? Well, if I were to just take a vertical line everywhere, it looks like a function to me, right? So yes. B, it might appear that we have a vertical, if we put a vertical line right here, that's a good vertical line. If we put a vertical line right there, then we're crossing the graph in more than one place, okay? But that's not true though, right? Because we know that this open circle right here tells us that the graph does not exist there, okay? So it's going, from here up to here, and then it stops at that open circle, and then continues to go through here. Okay, so B is also a function because a vertical line does not intersect. These Y's are just awful. Ugh. Let's try it again. Yes. Yes. Yeah, whatever. These are good. All right. Anyways, but if I take a vertical line to C, well, obviously we're crossing at more than one point, aren't we? So this would be a no. That's it. Vertical line test is pretty easy, isn't it? Ooh, polynomial functions. Okay, so page. Excuse me. So there are many different classes of functions that you will encounter throughout this text. Therefore, given a function, it is extremely important to learn how to classify it. So we need to classify what these functions are. So we start by introducing 3 classification functions: polynomial functions, rational functions, and root functions. Okay, and immediately, right, looking at rational, right, we've seen the word rational plenty of times in this course, haven't we? Rational means ratio, so we're looking for fractions. And root, all right, well, if we talk about roots, think about square roots, cube roots, things like that. So the last 2 are pretty easy, and honestly, the first one is easy as well, the polynomial function. All right, but the definition of a polynomial function. A polynomial function of degree n is a function of the form, all that mess, okay? And for any of you that are interested in going into mathematics, every time you write up a proof that involves a polynomial, you have to write all that mess. All right, so where n is a non-negative integer. So where do we see n here? Okay. All right, so we see n in a couple places. All right, we see n as a subscript, and we also see n as a superscript. Okay, so the definition of a polynomial, n has got to be non-negative. What does non-negative mean? Well, it means positive, right? Positive and 0, right? And a sub 0, a sub 1, a sub 2, a sub, all the way to a sub n are real numbers. So what we're looking for here is making sure that our exponent is not negative. Okay, if our exponent is negative, then we do not have as a polynomial function. Okay, so I think that about sums it up. Okay. Well, yeah. Let's just roll with an example first, because I feel like I might have a little ambiguous when I said a negative function. So actually, maybe I can do this. Actually, I'm going to put this on the same page. Current page. Okay, so example 7, determine whether a function is a polynomial function. Okay, so A, if we look at A and if we rewrote this just like the polynomial function. So what it does, is it looks like we are writing our function in descending order with the highest power and then the next highest power and the next highest power and so on and so forth. Okay, so if we were to write this in polynomial form, it would be, it would be f of x is equal to 5x cubed minus 3x squared plus 7. Okay, and it's not neat, but it doesn't have to be right now. So is this a polynomial function? Okay, yes, because if we look here, then we see our variables are indeed non-negative, right? We have x cubed. You can't really tell because, as I mentioned before, writing small numbers kind of hard on this program. Yeah, we'll just write a little bit bigger. There we go. Okay, so we look at our exponents, and we do indeed see that they are non-negative. Okay, so A is indeed a function. Okay, B, you don't have a variable there, do you? But you kind of do, right? B is saying h of t. H of t. Okay, so that's the variable being used. Well, think of B as being negative 11 times t to the 0th power. Okay, and what's anything raised to the 0th power? Well, that's 1, so it's 1 times negative 11, which is indeed negative 11. But that's not the point here. The point here is that we have a variable. All right, you can't see it. It's there though, but you can't see it. We have a variable, and it is indeed being raised to a non-negative power. Okay, non-negative being, again, positive or 0. And once again, I feel like the example that is contrary to the definition is the one that really drives the point home. So let's look at C. So f of t, we're going to rewrite this in descending order. Okay, so it would be 3t to the 6th plus, well, what is 1 over t written not in fractional form, right? That would be t to the negative 1 power. Okay, so now it should become abundantly obvious what we mean by our variables must be raised to a non-negative power. Okay, so we see that we have 3t raised to the 6th power here. Good, we're good there. But then we have a t raised to the negative 1 power. And that being raised to the negative 1 power tells me that, obviously it's negative, so therefore it's not non-negative. So C is not a polynomial. Okay, A and B are. So hopefully you remember your exponent rules, and you'll be just fine on those questions. Let's see this. Yeah, same thing I said. We're good. All right, rational functions next. Rational functions I think are a lot easier. I mean, honestly, I feel like they're all pretty darn easy, right? But this one is super duper easy. Rational function, same thing as a rational equation. Not same thing, but the same principle here. We have ratio, right, meaning fraction. So same principle being that we look for basically a fraction of polynomials. So do we have a polynomial over another polynomial? And that's all a rational function really is. Looking at the tip, if the degree of h of x is 0, then h of x equals c, where c is a real number, and we can consider the function right here. F of x is equal to g of x over h of x, and that's equal to g of x over c to be a polynomial function. Okay, so if we just have some real number as a denominator, then that's perfectly fine. That would still be a rational function. That's all that's saying there. Okay. I think we can put the example on here. Okay, so 8's pretty easy. I'm not 8. Example 8a is pretty easy, right? Obviously, it's a polynomial over a polynomial, so that it is indeed a rational function. Now B, now you you're probably expecting to be tricked here, right? But would you be wrong? Okay, because if I were to rewrite this, okay, and I want to get rid of that negative exponent, right? Remember, anything, we'll write x to the negative fifth. X to the negative fifth is the same thing saying 1 over x to the fifth, right? So if I were to rewrite this with a non-negative variable in place there, this would be x cubed, ugh, man, I hate this, x cubed, oh, that's not decent, 3, minus x squared minus 9 all over x to the fifth power, okay? Because this would be the same thing as saying being multiplied by 1 over x to the fifth, and then therefore it's just in the denominator. So it looks a little tricky, but b is also indeed a rational function. I don't think that we have really an example of root functions, and yeah. And the reason why is because it should be abundantly obvious if you have a root function, right? And that obvious part is that you have a root, okay? So the function f of x equal to the nth root of g of x is a root function where it is an integer that n is greater than or equal to 2. Okay, so what that's saying is we have a root higher than 2, square root, cube root, fourth root, fifth root, sixth root, so on and so forth. And then we see down there examples of root functions. All right, now we get to, the big one. This is where it gets really interesting. I don't usually snip that wheel this time. Domains, okay? So domains is a concept that you've heard many, many times, but I can almost guarantee you that you don't really fully understand all the layers of the domain of a function. Not yet anyways, okay? Or if you do, then you forgot because, you know, summer break's really long, right? So here's what we're looking at. How can we do this? Okay. Let's imagine this is some machine, okay? I mean, it looks like one, doesn't it? It's a machine. Looks like you put something in and then you get something out, okay? So let us just go ahead and define that, and let's say what we put in will be the input and what we get out will be the output. Perfect, okay? Okay, so the machine's name is going to be the function. Whatever function we have, it's going to be the function. What we put in, the input, the input is going to be my domain values. All the values of my domain. What am I allowed to input into this machine? Okay, so let's remember that. What am I allowed to put into this machine? Okay, because I'm going to come back to that in a moment. The output is what I get out of the machine after I put something in. Okay, so this is kind of a visualization of what a function is. A function is a machine, okay, and the abstract term here, space here would be the equation. Okay, so the machine is the function, all right, and whatever I put in is the domain, and what I get out is the range. Okay, so without trying to confuse you too much more, let's jump straight to a definition. The domain of a function, the domain of a function, y is equal to f of x, is a set of all values of x for which the function is defined. In other words, a number x equal to a is in the domain of f if y is equal to f of a is a real number. So again, what that's saying is what I'm allowed to put into the function. Okay, so real quick, let me just give you an example. Okay, so let us imagine. All right, little old Sherman, and I did do this actually, but I didn't take it as far as I'm about to. I'm building toy rockets. You know, I'm just having fun experimenting with things, and these toy rockets, they have something called engines in them, right? The engines are just basically just a solid propulsion that just it's like a firework, okay? And they're called engines. Well, here I am, I'm a little kid, I'm thinking, you know, maybe some great ideas pop into my head, and let's say I come up with some nice renewable energy, you know, for these engines, and I'm able to get more power out of these engines than what is normally available to us, right? So let's just say let's say that a normal engine in a toy rocket might look like something like this, right? Right? It goes up, it rotates out, and then it falls, it lands right here. Okay? Well, let's say that my new toy rocket engine, I shoot up way up here, and then I land right here. Okay? So my toy rocket engine is so much better than the one that you could buy at Hobby Lobby or wherever. Okay. All right. So here's the thing. We have this graph up here. Okay. We'll just call this height h. I should put that. No, we'll keep that in red. No, blue. Sorry. We'll just call this height h. All right. And this time, right? We'll just call this big T. Big T. Okay. Actually, no. Let's do this instead. Let's actually use hardcore. Let's actually use hardcore numbers. All right. Let's say that this goes. Whew, let's say that I'm a real big genius and I'm popping these things off at 1,000 feet. Okay. And let's say that the entire flight. Let's say the entire flight, lasts 20. Actually, I mean the descent. Whatever. Lasts 20 seconds. Okay. So this x-axis, okay, will be time, and this y-axis, okay, let's do this. This x-axis is time, and this y-axis is my height, okay? So anyways, let's see here. So I decide to, I graph this, I map it out, and I'm so proud of this, and I'm like, hey, I'm going to send this to some NASA engineers and see what they think, okay? Well, what they're going to do, imagine that this particular NASA engineer is a real jerk. He's having a bad day, so he wants to take it out on a little old kid. And he looks at this, and he's like, hey, this is cool, okay? But then he says, hey, okay, so what happens when t is equal to 25? What happens there, okay? Well, I'm like, nothing happens there, right? I mean, that makes sense, doesn't it? Because my toy rocket, it went up and down and hit the ground, and at 5 seconds after it's hit the ground, it's still right there, isn't it? Okay. Well, that's an example of domain, and it's probably a really horrible example with my NASA engineer and all. But I would say that the domain of this the graph of this toy rocket goes from right here at 0 seconds, and it goes all the way to 20 seconds. So if I were to have mapped out a function of this, okay, so I would say this function, it's like negative x squared or whatever, okay, but I'm just gonna call it alpha, right? Just an alpha, so some polynomial, okay. Then I would denote the domain would be from the domain would be from 0 to 20, okay, because let's erase that because I feel like I'm going off the page a little bit, and for the notes might be a little rough. So if x is equal to alpha, and my domain is 0 to 20. Okay, so golly, I hope I'm not losing anybody here. So here's the thing. I tell my NASA engineer, hey, this is my function. Okay, that's the function of the trajectory of my rocket. Okay, but in order to get the height of my rocket, okay, you can only figure out, you can only use the numbers from 0 to 20 because that's the domain. Right? The domain are all the values that I'm allowed to use, all the values that I can use, and therefore that is my domain. Okay, so if our NASA engineer, I don't even know why I say he was a little jerk, right? But if our little jerk NASA engineer said, well, what happens here at t equals 25? Well, he can't do that, right? Because I said, look, you can only evaluate this function from 0 to 20. Okay, because imagine had I not done that, had I not done this, then this function here would say that after, let's go out here, after 1,000 seconds, right? Well, let's do 100 seconds. After 100 seconds, if I were to follow along with that function, then this rocket might be halfway to China, right? It might have dug into the ground and that's all the way to China now, right? But that doesn't make sense, does it? Okay, and hopefully this really maybe hopefully ties together with what we're talking about when we say domain. Domains are values I can use, okay? But since I restricted the value of the domain of my toy rocket from 0 to 20, then you cannot ask what happens at 100 because it is not defined there, okay? Furthermore, you can't say what happens here at negative 20, right? Because it is not defined there, right? I cannot go back in time, right? So that's why we define functions. That's why domains have to be, that's why we define domains, right, of functions, because we have to say what we are allowed to use, and then we use it, okay? And to maybe tie in together with the previous page, we have to say what we are allowed to put into the machine. And in my rocket example, I'm only allowed to put in the numbers 0 through 20, okay? And if I put in 0 through 20, my machine, my function will work. But if I plug in any values outside of 0 to 20, then my machine will not work. And once again, I'm going to shut up because I feel like I just over-explain things sometimes. That's all nice, but we're going to do something even more fun. Okay. Perfect. And I think this might be towards the end, so we can talk about my nice. Okay, so we can talk about my domain Bible here. Okay, so we don't have to snip that just yet. This is super duper 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 important. If you have dozed off the last 65-ish minutes, you need to wake up. Okay, this is going to be the domain Bible, and I'm going to need you to put a star by it. Domain. Okay, I'll try to write this nice and neat. The domain Bible. Okay. So the domain Bible states, okay, I'm telling you, I call this the domain Bible because for all your domain needs for the rest of this class, for pre-calculus, for calculus, whatever you're doing from here on out, these few lines we're about to write down will take you all the way there. Okay, so the domain Bible. So here we go. Every function has the domain of negative infinity to positive infinity. Except in two cases. That doesn't look like cases at all, does it? Except, I guess it did. Okay, so except in two cases. Okay. So, first case. Okay, so here we go. So let's look at the very first line of this domain Bible. Every function has the domain of negative infinity to positive infinity. Period. Every single function. That is exactly where we start. We start with saying, okay, this function has the domain of all real numbers, except in two cases. Case number one. Okay. Case number one is if we have a variable in the golly, again, my heavy hand. Denominator. Okay. So this is case number one, as if we have a variable in the denominator. Okay, so let us look at an example real quick. Let's say we have the function f of x equal to, let's say we have the function x minus 3. Okay, so we're given this function. So we would say, okay, we're asked to find the domain. We're going to start here at line number 1. Boom, every function has a domain of negative infinity to positive infinity. That's where we're going to start. So first thing we're going to do is we're going to say this has the domain of negative infinity to positive infinity. All right, but then we're going to move on to the sentence with the except part, right? Except in 2 cases. If we have a variable in the denominator. Okay, so look in here, we indeed do have the variable in the denominator. Okay, so, well, this tells me that the domain is not negative infinity to positive infinity. Okay, so instead we're going to think about this logically for what we've done up to this point. Okay, so if we have the variable in the denominator, what we're going to do is we're going to think about, okay, so what cannot be in that denominator? Well, what do I know I cannot have in any denominator? I know I cannot have a 0. Okay, so what I'm going to do here is I'm going to figure out what I cannot use. Okay, so I cannot have x minus 3. All right, so x minus 3 is equal to 0. So I know that this down here cannot be equal to 0. So what I'm going to do is I'm going to figure out what value makes that 0. What makes that denominator 0? Okay, and it's not a hard leap to figure out that when x is equal to 3, when x is equal to 3 here, okay, then I have a 0 in the denominator, okay? Because 3 minus 3 is 0, I know I cannot use 3, okay? Now don't confuse this with saying I cannot have a 0 in the denominator, and therefore if x is 0, right? Because if x was 0, then 0 minus 3 is negative 3, and then we'd have 4 divided by negative 3, and that's perfectly okay, okay? So we look for what we cannot use, all right? So we set up the equation, equate it to what I'm not allowed to use, which is 0, and solve for it. Okay, so this tells me that the domain of this problem, let's see, I'm going to run out of room. Okay, so here we go. So this tells me that the domain of this problem, okay, is from negative infinity all the way to a positive 3, union with a positive 3 to infinity. Basically what this is meaning is that I'm allowed to use every single number but 3. Okay, so if I were to look at that on a number line, it's saying from negative infinity to 3, not including 3, union with 3 to infinity, again, not including 3. So that's the domain of the function. I set up the equation to figure out what I'm not allowed to use, and then I go from there. Okay, so let me see if I can move this toolbar out of the way real quick. Okay, so I don't think you guys can see the toolbar, so I think that's fine. All right, so that's case number 1. Case number 2, okay, is if we have, let's do that have again, have, okay, so here we go. So it's going to be a variable in an even, that's horrible, okay, in an even indexed radical. Try it again, radical. Okay, so if we have a variable in an even index radical, so what do these words mean? So let us look at the anatomy of a radical real quick. Okay, so we have the nth root of some number a, okay? I could say the radicand, but real quick, so this little symbol here we know as the radical, right? We know that's the radical, right? This inside here we know as the radicand, and this number here is the index, okay? The index or the root, okay? So what I wrote was if we have a variable in an even indexed radical. So what that's basically saying is if we have a square root, a 4th root, a 6th root, an 8th root, a 10th root, all the way to, you know, infinity, right? A 66th root. That is an even indexed radical. Okay? So if we have a variable in an even indexed radical, then we must solve. So let's give an example here. So let's have some function f of x and that's going to be equal to, let's say, the square root of, we'll stick with x minus 3. Okay? Okay, so what do I know I'm not allowed to have in a radical? Okay, so similar to my first case, what do I know I'm not allowed to have? I know I'm not allowed to have a 0 in my denominator. So for 2, I know, or for this one, I know I'm not allowed to have a negative number. Okay, so what I'm going to do is I'm going to put my radicand and I'm going to equate it to what I'm allowed to have. Okay, so for a variable in the denominator, I set up the equation to what I'm not allowed to have. I'm not allowed to have a 0 in the denominator, so I equate it to 0. Okay. For a radical, I'm going to set it up to what I know I am allowed to have. Okay. And honestly, let's see. Yeah, we'll stick with that. I was going to see if I can maybe make that easier on you. But we've got x minus 3 is greater than or equal to 0. So if I solve this for x, right, we would have x is greater than or equal to 3. Okay, so this tells me that the domain will be for all values of x that are, guess what, greater than or equal to 3. And that makes sense, right? Think of a number that is greater than 3, okay? Well, greater than or equal to 3. So let's just stick with 3 right now. If we plugged a 3 in here, 3 minus 3 is 0. And, well, the square root of 0 is 0, and that's okay. Okay, let's use 4. 4 minus 3 is 1. The square root of 1 is 1. So we're good, right? So this tells me that as long as I choose a number that's greater than or equal to 3, then it will work. Okay, and again, let's say if I pick 0, right? Well, 0 is not greater than or equal to 3. So if I plug a 0 in here, I'd get the square root of negative 3, and I know that's an imaginary number. So anyways, whew, this is my domain Bible. Every function has a domain, negative infinity to positive infinity, except in 2 cases. Case number 1, if we have a variable in the denominator. If we have a variable in the denominator, we figure out what we cannot use, and we proceed there. And number 2, if we have a variable in an even indexed radical. Okay, and what we do here is we set the equation up into what I'm allowed to use, and then proceed from there. And I know we're over time, but these lectures are recorded, so you can obviously watch them. So we're just going to continue on with our last example of the day here. All right, here we go. So first thing, jump straight to A. And honestly, I'm not even going to write A down, right? Because if we go by the domain Bible that we went over, okay, we said that the domain of the function is all the values that we, the domain of a function is negative infinity to positive infinity except for 2 cases. The first case is that if we have a variable in the denominator, and we don't, okay? And the second case is if we have a variable and an even index radical, which we don't. We don't have a denominator or radical, okay? So the domain of A is just simply negative infinity, positive infinity. So I'm just going to go and write that for A, because that's an easy one. Okay, shoot, let's make that prettier. Okay. Now B, okay, B is that first case, right? We have a variable in the denominator, right? So as we see, we have x squared minus x minus 6. We have that variable in the denominator. So what do we have to do here? Well, we have to look at the denominator and we have to figure out what we cannot use, okay? So in order to figure out what I cannot use, I know that I cannot have a 0, so therefore I'm going to equate the denominator equal to 0 and solve from there, okay? And if I do that, I've got so what, 3 and 2. Okay, so we've got x minus 3 and x plus 2 is equal to 0. And therefore, when x is equal to, we'll put it over here. When x is equal to 3 and when x is equal to negative 2, that's when my denominator is equal to 0. So these two are the numbers that I'm not allowed to use, okay? Because again, if I plugged in these numbers into this equation, I get a 0, and that 0 will make this denominator 0. Okay, so even though those numbers are the solution to the equation, they're the solution to the equation of this, what makes the denominator 0. And that's what I'm not allowed to use. I'm not allowed to have a number in the denominator that is 0. Okay, so therefore, my domain here, I'm going to try to save space here. So my domain is negative infinity to negative 2, unioned with negative 2 to 3, unioned with 3 to infinity. Okay, so we're going to re-snip all the problems here. New page. Excuse me. So C doesn't look fun at all. Okay, so we've done C-ish before, so let's do this. Okay, so C. So again, let's go back to my domain Bible. This is number 2. If we have a variable in an even indexed radical, okay, looking at C, it is indeed an even indexed radical because that is a square root, right? So we have the square root of x squared minus 2x minus 8. So what do I have to do? Well, what I did with my domain Bible was I set the radicand to greater than or equal to 0. Okay, so that's what I'm going to do here. I'm going to set it to x squared minus 2x minus 8 has got to be greater than or equal to 0. All right, and in order to do this, we're going to factor here. So we're going to have x. Let's not do it squared. So we're going to have 4 and 2. So we're going to have a negative 4 and a positive 2. Okay. So how do I figure this out? So we have two equations. We got x is greater than or equal to 4, and x is what would be greater than or equal to negative 2. Okay, this is not the correct way to do it, unfortunately. So I can't remember if we've done this. I'm pretty sure we have. Where we had the where we had to make walls. I'm pretty sure we've done it. Well, we had to have, right? Otherwise, we wouldn't be introducing it here. Okay, so this would be the wrong way to do it, is to set this equal to greater than or equal to 0 and solve from there. Okay, if you recall, we can only do that with the zero product principle when we are equal to 0. Here we are not equal to 0. Okay, so instead, what we're gonna have to do is I'm sorry, I really forgot the name of the procedure. But you only have to do this when what's inside this radical here, the radicand, is of degree 2 or more. Okay, so for the example I gave here for the domain Bible, example number 2, that is honestly what you're going to be seeing most of the time. You're going to be seeing a first degree polynomial as the radicand. When you see a second degree polynomial, that's when you are going to have to do this extra step. And it is a pain. I hate it as well, but it must be done. And yeah, I do remember doing this because I remember drawing this number line. Okay, so it looks like 4 and negative 2, so we'll do 0, 6, 7, 1, 2, 3, 4, 5. Okay. So if you recall, when we did this before, we had to look at this inequality, okay, and then we have to set up walls, right? And so I'm going to set up a wall here at x is equal to 4, and a wall here at x is equal to negative 2. So here at 4, 1, 2, 3, 4, I'm going to set up a wall, and at negative 2, I'm going to set up a wall, right? And then from here, I'm going to denote what the interval is. Okay, so from here is from negative infinity negative infinity to negative 2. That's awful. Let's try that one more time. Negative infinity to negative 2. And then this interval is negative 2 to, what was it, 4? Positive 4. And then this one is from 4 to infinity. Okay, so that's my 3 intervals. And we are going to pick a number in that interval. Okay, so we're going to pick negative 3 here. I've said before, if you have the number 0 available to you, use it. Okay, so in the interval from negative 2 to 4, 0 is available, so I'm going to use it. And then from 4 to infinity, we're going to use 5. Okay, so this is where we need to plug in these values into this inequality and figure out if it makes sense. Okay, so this is where we did the positive times positive is positive, positive times negative negative, and negative times negative is positive. So here we go. If I have negative 3 minus 4, that's negative 7. Negative 7, it's a negative number. Okay. Well, then if we have a negative 3 and a positive 1, well, that's a negative number. So if we did a negative times a negative, negative 7 times a negative 1, right? And honestly, you don't have to do the negative 7 times negative 1 in your head, because a negative times a negative is positive, and a positive number is greater than or equal to 0. Okay, so this tells me that this interval works. All right, well, let's plug in a 0 now. So 0 minus 4, that's a negative number. 0 plus 2, that's a positive number. A negative times a positive is a negative. And a negative number is not greater than or equal to 0, so this interval does not work. And then 5 minus 4 is positive. 5 plus 2 is positive. Positive times a positive is positive, and a positive number is greater than or equal to 0, and therefore this interval works. Okay, so this tells me that the domain of this problem are these two domains, are these two intervals right there. Okay, the ones with the check marks. So it is negative infinity to negative 2 unioned with 4 to infinity. Okay, and I'm going to do D, and I'm going to let you think about E. Okay, because we're very long here. So D, what's the domain of D? Well, it is a root, right? But it's an odd root, isn't it? It's a cube root, right? And if we go back to my domain Bible, I said if we have a variable in an even indexed radical rather. Okay, well, this is an odd index radical. Okay, so it does not violate either of these two criteria. Therefore, its domain will be from negative infinity to positive infinity. Okay, so this one is negative infinity to positive infinity. And again, E is a little bit trickier. You have to combine a couple things, but the solution is obviously in the textbook. But I'm going to end this lecture right now, and yeah, that's it. All right, so that's the conclusion of Chapter 3, Section 1.